Welcome everybody to the online seminar series, Machine Learning Needs Mathematical Optimization. So today we are extremely pleased to have Adam Elmachtoub. He is an associate professor of industrial engineering and operations research at Columbia University, where he is also a member of the Data Science Institute. And he's currently a visiting academic at Amazon. His field of specialization are prescriptive analytics, machine learning, revenue management and pricing, and supply chain management. Adam has published in the leading journals in the field, such as management science, mathematical programming, mathematics of operations research and production and operations management. And he has appeared on mass media outlets such as CNN and US News. He has received several prizes for his research, such as the NSF Career Award, IBM Faculty Award, and he is on the Forbes 30 under 30 in science. His professional service list is quite long, and I would just mention that he is in the editorial board of several journals in the field, such as management science. So we are very pleased that you could squeeze us in your busy agenda. And for the audience, please remember that Adam is happy to take questions on the go, and you can put them in the chat. And if you want to, you can also wait until the Q&A session at the end, where we will give you rights for the camera and the microphone. Thank you so much to everybody.
All right. Thank you for the very kind introduction. It's wonderful to be talking to this audience. This is an excellent area of research to be in. So I think everyone in this chat is doing great work. And like Dolores said, please feel free to ask me questions throughout. So my talk today is I designed it more to be like an introductory lecture, as I would do in a PhD course. So I'm going to go very, very slow and not even going to talk about my research until maybe like halfway through, because I really want to talk about more about the area and the problem and sort of motivate you to look into this and understand why it's important. Okay, so the title of the talk is called Smart, Predict, and Optimize for Contextual Linear Optimization. And hopefully you'll understand what all these phrases mean soon. Okay, so let's get into it. Before anything, I'd like to acknowledge that this is not solo works. This is collaborative works that I'm going to talk about. Paul Grigas is my co-author on the first paper in this topic. And we have Ambuj Tewari and Othman, who will collaborate on a second paper on this topic, and Ryan and Jason, who are also former students, collaborators. So really appreciate all their help. And this is all joint work with them. Okay, so what is contextual optimization? So many of you might know this by now, but the idea is like this is sort of a way to marry machine learning and OR problems together. The general concept is that you have an optimization problem you want to solve, but you don't necessarily know all the parameters. And what you do have is some contextual data. So these are like what you might call them features to predict unknown parameters. Okay, so this represents many OR and analytics problems in practice. Anyone who works in industry, or any of your students who have gone on to industry, will have done some kind of contextual optimization at this point. Okay, and today we're going to focus on a particular class of problems where the objectives are linear. Okay, so this is like the starting point for any optimizer, linear objectives, and they have lots of use in practice. Okay. So let me give you some examples of contextual optimizations of linear objectives. So here's like 3 fundamental problems. And note that when I say contextual linear optimization, I just mean the objective is linear. So the feasible region can be convex, it can be integer program, anything is fine. So the first example is a classic inventory management problem called economic lot sizing. There you have to like satisfy a sequence of demands. That's the constraints. And your objective is to minimize the total ordering and holding costs and maybe backlogging costs. Okay, can people hear me? I'm seeing like a bunch of people saying they don't have sound.
Yes, we can hear you. A couple of people cannot hear, but they probably need to give rights to their own sound. Yes, so you can see that most of us can hear. So I will try to solve the problem for the other two. So please go ahead.
Okay. So the context here are that when you're solving these deterministic lot sizing problems, you have to input the demand. Okay, and how do you predict demand? You usually have information about the seasonality, orders, search history, similar product sales, and so on. Okay. And here the unknown parameters appear in the objective, the demand constraints, and the constraints are they satisfy all demand. Another example is like the traveling salesman problem or vehicle routing problems. There, the objective is that you have to minimize the sum of the edge costs. And what is the unknown parameter? Here, instead of demand, it's like the time it takes to travel on each edge, or maybe the cost of each edge. And you have to put constraints that are basically network flow constraints of some kind and cycle constraints. And here, what are the features or contexts you use to predict the unknown parameter? It could be like time of day or holidays or speed limits and things like that. And then finally, like a nonlinear constraint example is like portfolio optimization, where you have to maximize the expected return of a weighted collection of assets. But what is the unknown parameter in this setting? It's the return of each asset. So we need to predict how successful each investment is going to be. And you might have constraints on how much risk you're willing to take, like the standard deviation of the portfolio. How do you predict? Well, the contexts here are going to be like returns, historical returns, social media, news, economic indicators, and so on. So this is a very fundamental problem. It appears in all kinds of settings. All right. So what does predict and optimize mean? This is basically the standard way that we go about solving these problems. Believe it or not, this phrase did not exist before our paper. So even though it's like a standard thing, so now the phrase is kind of standard as well. But the predict and optimize simply means you use a machine learning model that takes the context and predicts the unknown parameters like the demand or the costs or the asset returns. And then you plug in those predictions into the optimization problem and then you solve it. So that's what predict and optimize means. And that's what people have been doing for a long time. Now, the fundamental thing, if there's one thing I want you to take away from this presentation, it's that as OR scientists, what we should be thinking about is minimizing decision error and not prediction error. Okay, and that's really what motivates this whole field. Okay, and why is there a difference? We'll talk a lot more about that, but fundamentally what's going on is that machine learning models are built to minimize prediction errors, which may or may not be aligned with the decision error. So what are the contributions that I'll talk about? Basically, we design a so-called smart predict and optimize framework. And why do I call it smart? It's because we take into account how the predictions will be used as an input into the downstream optimization problem. And we're going to do that by designing a new loss function. We're going to call that the SPO loss function. It's also going to be a very general framework. So basically, we can handle any scenario, any kind of problem that I mentioned, but any tractable problem with unknown linear objective. And we can train linear models, decision trees, and so on with this framework. So it's computationally tractable, and we've implemented it. We also have important theoretical guarantees, which I think really validate and explain why the approach seems to work very well. And I'll talk a lot about those too. And finally, like we'll show that this really outperforms standard predict and optimize approaches, even when, for example, we use like a linear model and compare it to like a random forest or neural network using a traditional approach. So I want to highlight some pre-existing work before we started this research. And there's too many papers that happened afterwards. I'll mention those at the end a little bit. But, you know, you can look back up to like maybe this 97 paper by Bengio, where they try to train a neural network, not to minimize prediction error, but to minimize some financial criteria for financial engineering. This paper by Cao, Van Roy, and Liang, they look at this SBO problem, but more for like an unconstrained quadratic optimization. There, everything can be done in like closed form, but it doesn't allow any constraints. And in many applications, there are constraints you have to deal with in your optimization problem. Bon and Rudin have this nice paper called the Big Data News Vendor, where basically they say like, hey, let's choose the news vendor quantity as some direct decision based on the features. Okay, so there's no predict and optimize. You just go straight from features to decisions. And there again, they do not have any constraints. And I'm emphasizing this because constraints makes the problem much harder, and you cannot just go directly from context to decisions when there's constraints, because you have to worry about feasibility. Then there's this paper called by Bertimus and Callis called like Predictive to Prescriptive Analytics. And there they basically say like, look, you can like you can use the same old machine learning techniques, but just kind of alter how they get used. So a lot of them output these weights, and you can weight the historical cost functions using these weights, and it's better than just using a point prediction. Unfortunately, though, they don't. For linear objectives, their approach is exactly equivalent to normal predict and optimize. So their approach is really only helpful for nonlinear settings, and they don't train the weights based on the downstream optimization problem. Okay. So our approach is very different than these pre-existing works, and it's also very related to like many other areas like SAA, stochastic and robust, and inverse optimization, and so on. All right, so let me get into the mathematical model. What exactly is contextual linear optimization? Let's talk about some notation. So the context, we're going to call it X. Okay. Every time you see a new X, you want to make a decision W. So W is going to be in this feasible region denoted by S. So this is my constraint body. And my objective is linear. It's C transpose W. Okay. But there's this expectation around it because this is a really stochastic optimization problem, because C is a random variable. The cost is a random variable. That does depend on the features X. Okay. So X could be, so if we're thinking about, let's say, the shortest path problem, C is like the time or the cost of each edge, and X is like the speed limit, historical costs, and the traffic and holidays and things like that. Now, by linearity of expectation, we can rewrite this in a deceptively simple way as expected value of C given X transpose W. Why is this interesting? Because basically it highlights the fact that really predict and optimize is the right way to go about this problem. So what we want is a prediction of expected value of C given X. Okay, if we knew expected value of C given X, we're fine. Now, note that if the objective is nonlinear, we would require a distribution of C. We can't just use the expected value. So in the nonlinear setting, we think about estimate on optimize, where we're estimating a whole distribution. In the linear setting, it's really just about this point prediction. Now, unfortunately, in reality, you don't have the distribution of C given X, right? You can't just look it up in a book or on a website. Instead, we have data. Okay, so really the problem looks like this. So there's 4 ingredients. the first ingredient is, what is the downstream or nominal optimization problem we want to solve? It's, again, it looks something like this. So it's for any cost vector C, you want to minimize C transpose W with W and S. So S is the feasible region, and we'll let W star of C be like denote the optimization oracle. So it can, and think about, if there's multiple solutions, it just spits out an arbitrary solution for the purpose of this talk. And instead of a distribution of over C and X, we have training data. So X1, C1 up to Xn, Cn. So the features and the historical cost vectors. And you also need a hypothesis class of prediction models. So how are you going to predict C from X? You have to first choose a class of models. So H could be like the set of linear models. It could be the set of neural networks, random forests, decision trees, and so on. And we'll typically put a hat to denote a prediction. So for some function f in your hypothesis class, f of x is like a prediction. And we'll use like c hat to denote that it's a prediction. Okay, but f is a model that maps from context to cost vectors. And finally, what you need is a loss function. A loss function measures what is the error when we predict c hat when the real value is c. Okay, so the classic loss function would be the mean squared, would be like the 2 norm squared of the difference. So c hat minus c squared. So this is like least squares or mean squared error. Now, if I just gave you ingredients number 2, 3, and 4, this is like just standard machine learning. Okay, this is what intro to machine learning is, ingredients 2, 3, and 4. So we all know many, many methods for this. The difference is I'm also telling you ingredient number 1, which is like how this prediction is going to be used. Okay, and the way we're going to integrate ingredient number 1 is into the loss function. So we're going to create a loss function that takes into account ingredient number 1. All right. So what does predict and optimize mean? Putting all the notation together. So first, you train a prediction model by doing empirical risk minimization. So what does that mean? You basically average over the training error. So what is the training error? 1 over n, sum over the n samples, the loss of f of xi, comma ci. So ci is the real value, and f of xi is the predicted value. And you're going to choose f from your hypothesis class to minimize this training error. Okay, and you can also add regularizer if you want. Once you have this prediction model f star, then every time you see a new x, you plug in x into the prediction model f star, and then you plug in this cost vector into w star to get your decision. So this is predict, then optimize. Now, like to ground it in a setting we all know, least squares linear regression would be like you're minimizing over all matrices B. So B maps from feature vectors to cost vectors. You're minimizing the 2 norm squared of the difference. This is the residual squared. And once you get this best least linear mapping B, every time you see a new x, you multiply B star times x, and then you plug that into the optimization oracle to get your decision. So that's predict and optimize. Any questions about the framework? All right. I don't see any, so I'll keep going. So what is the loss function we're going to use? It's called the SPO loss function, and I'll derive it in 2 steps. So first, note that if we know the true cost vector C of our problem, the best possible decision we could have made is W star C. And this would cost us C transpose W star C. But instead, we have some prediction C hat. And what we're going to do is implement the decision W star of C hat. And this is going to cost C transpose W star C hat. So C here is the ground truth. is the real cost. So although we implement W star of C hat, we still collect the real cost. So the difference of these two things is the SPO loss function. So on the left-hand side is the cost I actually incurred because I implemented the decision C hat. On the right-hand side is the best possible cost if I implemented W star of C. Now, this is a not completely formal definition because tie breaking is very important. But in particular, like if I plug in C hat equals 0, then all solutions are optimal, right? So in order to avoid degeneracies, you have to define tie breaking formally. And we do that with like a worst case, in a worst case way. But I'm going to skip those details for this talk, and you can see them in the paper. But if you neglect that, you can easily, it's not just a theoretical issue, it's actually also a practical issue. Okay, so geometrically, this picture, I think, gives you a lot of intuition, and I'm going to explain it slowly. So let's say your true value is C, okay, and I'm plotting negative C. The reason why you see negative signs is because we're thinking about minimization problems. And this gray triangle is a cone for this extreme point. Okay, so any cost vector in this cone lead to this extreme point being optimal. Okay. Now, ideally, we would predict C hat to be C exactly, but of course we can't because data is noisy and that's just not possible to do perfectly. So let's say we have two candidate predictions, like one is C hat A and one is C hat B. And these predictions are actually both equidistant from C. So they have the same mean squared error. Exactly the same. So from like from the prediction perspective, they're equally good. Okay, and all models, are going to have some error. Now, which one is actually better from the decision perspective? If you predict C at A, because it's in this gray cone, we get back the same extreme point, and the decision error is 0. If you predict C hat B, you're outside of the cone, and it turns out the optimal extreme point is down here, and you make some decision error. So the loss here is not 0. So even though they have the same prediction error, the decision error is very different. And the SPO loss is capturing this exactly. Another way to think about it is like, the way I like to think about it is that all machine learning models are wrong. Like, they'll never be perfect. But sometimes we can be wrong in the right direction. And that's what's happening here. So C hat A is wrong and C hat B is wrong. They're both equally wrong. But C hat A is wrong in the right direction. So if you predicted the C hat A, you would get 0 loss. And that's what we want to exploit. Now, this is not just unique to like polyhedra. You can also think about convex regions. The story is similar. So here, the only way to recover the exact optimal solution would be for C hat A to be a multiple of C. Okay, that's why they align like this. Any difference we can cause some error, and the more different they are, the more the more error there will be. Okay. Any questions on this? All right, like I said, I'm going to do a lot of motivation before I actually talk about research. So let me give you a very illustrative example. This is the simplest possible example I can come up with to illustrate some points. So this is a shortest path problem. You're going from S to T, and you can either take edge 1 or edge 2. That's it. And we have one feature. That feature helps us make a prediction on the cost of edge 1 and the cost of edge 2. And I'm going to compare the least squares approach and the SPO approach. Okay, so least squares is like the standard machine learning approach. So first, let us talk about what is an error or a residual in this example. Like, let's compare what least squares does and SPO does. So on the left is least squares. So look at these white circles and these white squares. These are like the true costs I have. All right, that's the y-axis, and the x-axis is like x. So if I was doing linear regression, what I would do is I would fit a line to the circles, and I'd fit a line to the squares, and that's my those are my predictions. Okay, so the green line is my predictions for edge 1, the red line is my predictions for edge 2. And what least squares and regression is trying to do is to minimize the sum of these residuals. You can see them by the dotted red line. So the residual here is from the predicted value to the true value. Okay, predicted value to the true value, and so on. What does the SPO residuals look like in Smart Predict and Optimize? Very, very different. So let's start with the first sample point here for this X1. So here we're predicting, so we have the same two lines, but the residuals look different. So for the first point, we don't see any residuals. Why is that? So we're predicting that edge 1 is lower than edge 2. Sorry, the cost of edge 2 is lower than the cost of edge 1. And in the real data, the cost of edge 2 is lower than edge 1. So because our predictions are consistent with reality in terms of the ordering, then the optimization problem would choose edge 2. And therefore, there's no decision error. In contrast, in the second scenario, we do make a mistake. So here we predict edge 2 is cheaper than edge 1. But it turns out in this sample, edge 1 is actually cheaper. So because the predictions are ordered like this, we would choose edge 2, and therefore we'd make a mistake. And the cost of the mistake is the distance from the square to the circle, the white square to the white circle. So it's the cost on the real, the error is the difference on the real costs. It has nothing to do with the actual predictions, unlike least squares. So we're really measuring the decision error. Okay, so we want to, so the goal of SPO is to minimize the sum of these black dotted lines. Now let's try a bigger data set. So here, clearly I'm generating data artificially, just again for illustration. And let's say, the data is generated in this way. Again, we have one feature. And the optimal decision boundary is this dotted black line. So if you're to the left of the dotted black line, clearly you should take edge 2. If you see an x greater than 1.25 to the right of the dotted line, then clearly you should take edge 1. All right, that's the ground truth of what's going on. Now, let's say we fit a linear model here. It's like a natural thing to do, and these are the linear regressions for the two data sets. So for edge 1 and edge 2. All right, so you fit these two linear models, and then you see where they cross, and that becomes a decision boundary. So where these guys cross the decision boundary, and you can see in between these dotted red and dotted black lines, we're going to make some errors. So here, in between, edge 2 is cheaper than edge 1, although our prediction is suggesting the alternate. So between these two bars, we make some errors. What happens in SPO?
Adam, there is a question in the chat.
Yes, I see it. And this will address the question too. So what happens in SPO is that we are trying to minimize the decision error, not the prediction error. Okay, so that's what the question's asking. Yes, we are minimizing decision error. And so here we choose the linear models to minimize decision error. And this is what happens. So these are the linear models that get chosen. And you could see they intersect in a way such that there's zero error. Okay, so because it recognizes that there is a way to get zero training error, it does find it. And it's not the only solution here. There's actually many solutions. So here's another solution, for example. So it turns out there's many ways to draw two lines in this example, because basically it's like a very simple scenario where everything is perfectly separable. Now someone wants me to go back and understand what's the dotted black line. Again, this dotted black line is just saying this is the optimal decision boundary. You have to choose edge 1 or edge 2. So depending on what value of x you see, if x is below the dotted black line, you're going to take edge 2 because that's cheaper. If you see an x greater than 1.25, you'll take edge 1. So this is just like the ground truth where the simulation is coming from. Okay, so basically SPO recovers this perfectly, and least squares cannot do that because there's some model. So even though the ground truth is nonlinear, we can still get perfect resolution here. Let me show you what happens with decision trees. So let's say you take the same data set, and I just moved it out here to make a cleaner picture, and you fit a decision tree. So again, the dotted black line is the optimal decision boundary, and the gray lines here are the true costs. So if I fit a decision tree using the standard CART algorithm with depth 1, what happens is I split around 0.65. To the left of 0.65 and to the right of 0.65, I have different predictions, but in both scenarios, edge 1 is cheaper. Okay, so what that means is like my decision boundary becomes at 0, and it's saying like no matter what I do, I'm gonna always predict edge 1 to be cheaper. So basically, I always pick edge 1. Whereas, so clearly, in this region here, I'm always making suboptimal decisions. Now, decision trees are nice because they're universal classifiers. So what we can do is like increase the depth, and eventually we'll recover the line perfectly. So for example, if I increase the depth up to 4, then I can create 16 little segments. And now I'm approximating these true cost curves very closely. And you can see the decision boundary is converging. And now we're like almost optimal. All right. And again, and CART, if you don't know, it uses just like a standard prediction error as the splitting criteria. Now, why is this interesting? Because the SPO tree, when you're going to train a tree using the SPO error, the decision boundary gets recovered in exactly one split. Okay, so we actually perfectly can figure out this decision boundary because we're using the direct knowledge of the optimization problem to make our decisions. Okay, now you might say like, okay, well, we were able to get it anyways with depth 4 versus depth 1, but the whole point of trees is that they're interpretable, and a depth 1 tree is much more interpretable than a depth 4 tree. Okay, and in order to do higher depth, you would need more data. So that's another issue. All right, so I'm going to come back to these later on. Someone asked if SPO gives better predictions. The answer is no. SPO does not give better predictions. It gives better decisions. That's the point. All right. So hopefully I've motivated the fact that SPO loss makes a lot of sense. So what we do now is like, circling back is like, we're now going to plug in the SPO loss function into the empirical risk minimization. That's what we're going to solve. It turns out this thing is like highly non-convex and very difficult to solve. And that's why I'm probably not the first person to have thought about this problem, but it turns out it's a very, very hard problem. So the research is in really, what are the properties of this problem and how do we solve it? Okay, just to give you like some intuition, this problem is a generalization of 0-1 classification, which we know is NP hard and very challenging to solve. So I'll focus on two cases of like linear regression decision trees today in terms of like how do we actually solve the smart predict and optimize problem. Okay, so in the remainder of the talk, I'll first just do one slide on some theory of why does ERM principle even makes sense here. Then I'll talk about doing linear regression with SPO loss via convex approximation, and then decision trees with SPO loss using a direct approach. So why ERM? And this is a somewhat abstract slide if you're not familiar with this kind of theory, but it is important. So a fundamental property of any machine learning method is like how well we do out of sample on the test error compared to the training error. And to bound these, the bound between test error and training error is often called the generalization bound. So we can actually theoretically prove that a lot of algorithms have good generalization bounds. Basically, you want the training and test error to decay at a rate of like 1 over square root n. Okay, so basically what we can show in one of our papers is that when the feasible region is a polyhedron, the generalization bound decays at a rate of 1 over square root n. It also depends on the dimension d of the features. Of the problem, and p is the dimension of the features. And it also depends on the log of the number of extreme points. So because the number of extreme points can be exponential, it's nice that it depends on log number of extreme points. So this is a good thing. Now, what if S is not a polyhedron? Then the number of extreme points could be infinite if it's like a smooth body. So we also show that when S has this like nice strongly convex property, we can remove the dependency on S in our generalization bound, and we can show some like Lipschitz-like behavior, which is really nice. Okay, so that's just, for those who are interested, you can check out those results in more detail. Let's move on now to doing linear regression for SPO loss. So remember, the ERM problem is non-convex. So we basically want to get around this somehow. It's tempting to just sort of not care about the non-convexity nowadays and just throw it at some kind of solver and do some, just hope for the best. But any solver that's using any kind of gradients is going to fail miserably on this problem. It's a super hard problem because all the gradients are zero pretty much everywhere. Why are all the gradients zero? Because let's say like you have this prediction C hat A, right? If you imagine like I'm perturbing my parameter choices a little bit, then C at A moves a little bit around. But you can see if C at A, if you wobble it in any direction, the optimal decision corresponding to C at A is still the same. So the loss doesn't change at all. So any wiggling around here doesn't lead to any change in the actual loss. So the gradients are zero. So it's a very ill-behaved problem. You need a different approach. I'm going to talk about my approach, and there are other approaches that came out since then, which I won't have time to talk about. But my approach, our approach, me and Paul, that we came up with is called SPO plus loss. And this is a convex approximation to the SPO loss. Okay. And I don't want to spend too much time on the derivation, but I want to give you a little bit of insight to show you that it's not like completely crazy. And I think it's really the right approximation for several reasons. So first, how do we derive this SPO plus loss? So recall the definition of the SPO loss here. The first trick we do is we add 0. Okay. So Rezia, the whole rest of the talk is on solving the SPO model. So that's what we're talking about now. So that's really what the research is about. How do you solve the SPO problem? Okay, so the first approach, as I mentioned, is like to replace this non-convex loss function with a convex surrogate. That's what we're deriving now. So the first step is you add 0, and then you could do some clever rewriting, and you get this different way of writing the SPO loss function, which is basically a notion of strong duality. Okay. So this first equation, think about it as like a strong duality result. And just to give you a sense of like what this alpha is, just like imagine alpha is really, really big. then the dominant term is negative alpha c hat. And since we're maximizing, this is equivalent to minimizing c hat transpose w. So when you plug in the optimal solution here, you'd plug in w star c hat, and then everything cancels out back to the original SPO loss function. So with this different way of writing SPO loss, you plug this into the ARM problem, and now there's an index I for every sample I. So there's an alpha I, a wi, a ci, xi, and so on. Okay, so and here f of xi is replacing c hat. So that's our predictions. And the first trick is that because all the alpha i's are going to infinity, we can just make one alpha that goes to infinity. The second trick is that because alpha is being multiplied by f everywhere, we can just completely remove the notion of alpha to begin with. And we use the fact that this problem is linear, so here we can add an alpha in this w star f term. So w star alpha f and w star of f are the same. And then finally, we replace this like second term, which is non-convex, by the first order approximation, which is linear in c hat. So at the end of the day, the SPO plus loss function looks like this term down here. Again, I don't expect you to follow all the details, but you can check those out in the paper, but just give you a little bit of intuition of how this comes from. So basically, we use two key concepts in this derivation. One is like duality principles, and the other one is like standard machine learning engineering tricks. So to Rezia's direct question here. So now with this convex loss function, what can we do? So it turns out when S is a polyhedron, I can train a linear model with SPO plus loss with just a single linear program. So everything reduces down to a single linear program, which is really nice. Let's say S is like a convex body, or you want to use a neural net or something, or N is large, you can actually just use standard subgradient descent, and it works really well. Okay, so that's how it's solved in practice. Okay, and there are a bunch of tricks to speed it up. Oops, I had some citation here for from Gunz's lab, but I lost it for some reason. Okay. Now let me tell you like what this SPO plus thing is, kind of at a more intuitive level. So I give you like the math derivation. Here's like a different intuition of what's going on. So if you're familiar, if you've taken a machine learning class, I hope you've seen this picture on the right before. So in classification problems, you're interested in this 0-1 loss, where either you get it right or you don't get it right. But these are non-convex, and we don't minimize them in practice. Instead, we minimize some approximation. So this hinge loss is a standard approximation, and it's like at the root of the support vector machine method. And one interesting thing about the hinge loss is that as you have enough data, and if your hypothesis class is rich enough, minimizing the hinge loss is equivalent to minimizing the 0-1 loss, which is like why it works well in practice. And we can show basically that for a very, very special case of our problem, if you just say S is like a one-dimensional interval and C takes binary values, then we exactly recover this setup. So SPO would be the 0-1 loss, and SPO plus is the hinge loss. So basically, we completely generalized SVM to a whole new set of problems involving linear optimization. So the big question is, though, is SPO plus consistent with respect to SPO loss? Like, do we have this beautiful property that hinge loss is where hinge loss converges to the right solution? Does it also happen for SPO plus? And the answer is yes. So again, what's the setup? So the idea is like, let's assume I knew the full distribution of X and C. And let's assume we can use any prediction model we want. The question is like, will the best solution for SPO plus converge to SPO? And the answer is yes. So the best minimizer of SPO plus is equal to the best minimizer of SPO. And it turns out this minimizer is the expected value of C given X. So this should not be surprising, although it's actually really nice intuition. The best thing you can do, if you could do anything, is to predict the expected value of C given X. That is what shows up in the objective function. And that is what SPO plus does. So even though it's not the direct loss function, it still converges to the right concept, which is the expected value of C given X. Now there are assumptions required to prove this. We need that C given X is continuous to ensure this happens, and we also need that C given X is symmetric around its mean. And I just say that both assumptions are alone are not sufficient, and the standard setup that where these assumptions hold is to just say like C is equal to some function plus Gaussian noise. So if you believe that your noise is like Gaussian, then you would satisfy these assumptions. Okay, so this consistency property really justifies the SPO plus is kind of doing the right thing. Now, let me circle back to like least squares loss function, right? This is the standard predict and optimize loss function. It turns out least squares is also consistent. So in your undergrad probability class, you probably remember at some point, you might have even proved this, that the minimizer of the least squares loss function is the expected value of your target variable. Okay, so it is the expected value of C given X. So both are consistent, least squares and SPO plus. All right. So at this point, you should be saying, why has this guy been rambling for like 50 minutes and he's wasting my time? And if least squares is also consistent, why are we bothering SPO plus? Okay, why are we bothering with it? No, we did not waste our time. The whole point is that SPO plus is just as valid as least squares from a theoretical approach. So you should not think that least squares should be the standard one. And in fact, they're both equally valid. But from our logical derivation of us using the downstream optimization problem, it's actually going to work a lot better in practice. So SPO is going to outperform least squares when we're solving contextual linear optimization problems. And this result about consistency only applies when you have like no model misspecification. In reality, you always have model misspecification. Okay. And therefore, all machine learning models are wrong. And as I said up front, like it's better to be wrong in the right directions. So we're going to see that SPO plus does better from a practical perspective. All right, and there's been some follow-up theory to show that both least squares and SPO plus are not just consistent, but they're provably calibrated with SPO, meaning that like as the errors get smaller on these surrogate loss functions, the error on the true loss function also gets smaller, which is really nice. So it's not just an asymptotic result. Okay, so let's look at some experiments. So let's just say I generate the features randomly, and I have a cost vector that's just some polynomial in the features raised to some degree plus some noise. And the problem I'm trying to solve is a shortest path problem. So in your mind, I want you to imagine like a 5x5 grid, and we're going from the southwest corner to the northeast corner on this 5x5 grid. So there's like exponentially many ways to go, and we have to find the right one. And I'm going to train some linear models with respect to SPO plus, least squares, absolute error. Also going to try random forests. And we'll try out a bunch of simulations and different training data set sizes and different degrees of misspecification. So this degree parameter tells me like how much misspecification there is. If it's 1, it means that C is linear in X, in expectation. If it's greater than 1, it means there's some misspecification going on. Okay, so let's say the training set size is only 100 and the noise is like half. Okay, on the y-axis here is the SPO loss. So this is my decision error. And on the x-axis is the degree of misspecification. So 1 means that there's no misspecification in the model. So like the true data is linear in x. And the green is least squares, the purple is SPO plus, and the blue is random forest. So when there's no misspecification, pretty much everything does similarly. And in fact, least squares does slightly better. Okay. As you increase the misspecification, let's go to this extreme. It turns out SPO plus is the dominant strategy. Okay. And random forest is doing the worst. Is not surprising because the training data set is only 100 and random forests require a lot of data to perform well. And least squares is much worse. So SPO plus is dominating even random forests here. So someone asked, what does model is misspecification mean? I'll recall to you again that it just means that the model you're fitting is not what the ground truth is doing. So if I'm fitting a linear model and the data is not linear, this is called misspecification. So in reality, there is always misspecification. So if you're fitting a tree, you're assuming the data is coming from a tree, but in reality, it's not. It's just an approximation. So here, when degree is 1, I'm simulating so that there is no misspecification. So I'm fitting a linear model and the data is linear. So when the degree parameter is 8, the data is coming from a degree 8 polynomial, but I'm still fitting a linear model. And what happens is I increase the training data set size to 5,000. You can see that, okay, the purple and the blue are now similar. So random forests and SPO plus are pretty much the same now. And what's happening here? So as I boost up the data to 5,000, random forest is indeed converging as it is a universal classifier. But SPO plus is doing pretty much just as well. So it's a linear model, and it's pretty much doing just as well as a random forest, which is not an interpretable method at all. Okay, a linear model is very simple to state. Okay, so you see 2 benefits here. One is like either you're doing strictly better than the traditional approaches. And by the way, the standard least squares objective is doing really badly. And same with the absolute loss error. Okay, so the idea here is that if you train a linear model with the right loss function, you can do just as well as like a black box model like random forest. So that's really exciting for anyone that cares about simple or simple policies. Okay, but if you don't have a rich enough data set, then you can't even use random forest to begin with. So the sort of SPO plus model seems to be the robust one. Okay. Again, the x-axis here is the degree of misspecification. So 8 means the degree polynomial. The data is coming from degree 8 polynomials, and the y-axis is the decision error. So this is the SPO loss. So lower is better. Okay. Good. So I just have 5 more minutes. So the last part I want to talk to you about is decision trees. And I'll skip the algorithmic part just to say that basically we can build trees by in a way similar to CART, but using the downstream or optimization problem. We can also think about an integer program approach. And on the I'll look at the same exact data set as before, the shortest path problem. And here's like one results. So if I have 200 samples and I have some misspecification, so the data is coming from 10 polynomials of degree 10, you can see the SPO trees in blue are outperforming the CART trees by a lot. And what I'm plotting here on the x-axis is the training depth of the tree. So how many nodes, how many leaves in the tree. And in the unlimited case, I'm doing pruning as well. So I'm doing a cross-validation with pruning for both approaches. Okay, so the reason why we're outperforming CART here, even though trees are universal classifiers because the data is limited. So when I have limited data, I can't just train a tree to infinite depth. But the SPO trees use the data more intelligently, so it can get better decision errors. But if I increase the number of samples to like 10,000, which is like essentially infinite for this problem, and I allow unlimited depth, then the CART and SPO trees perform pretty much the same. And so this is for degree 2 and degree 10. Now, does that mean there's no advantage to SPO trees? That is false. So what happens if I look at the number of leaves in the tree, you can see that the blue, again, is SPO trees. I have about 1/3 the number of leaves as the traditional CART tree. So for the same performance on decision error, I can use a tree that's 1/3 the size and therefore way more interpretable, less than 100 nodes, which is manageable. Okay, and same for the degree 10 case. So CART will use like 250 to 300 leaves, and SPO trees is around 100. Okay, so in one extreme of the problem, when I have limited data, SPO gives me better performance. On the other extreme, when I have a ton of data, SPO gives me more interpretability. So in either scenario, I am benefiting. Okay. And again, CART was just the standard way we train decision trees. It's stands for classification and regression trees. It's like a greedy algorithm that works pretty fast and uses a prediction error to minimize the cost of the tree. Okay, so let me wrap up in my last 2 minutes. So Smart Predict and Optimize, I think, is a very useful framework, especially when there's linear objectives. I do have some work on nonlinear setting that you can check out my website, and there's a lot of other work in the field about this. What I want to emphasize is that SPO also has really nice theoretical properties. So we proved generalization bounds. We showed SPO plus is consistent and convex. And we showed that you can train simple interpretable models like linear decision trees, and they can outperform things like random forest and neural nets. I didn't show the neural net results because on these data sets, the neural nets don't work well. And there's so many more applications. Like here's just 2 follow-up works where people are implementing like a lot of new methods. I want to shout out this paper by Tang and Khalil, where they implemented an entire software package called Paiepo. And if you're interested in this, you have to go and look at this package where they implemented everything for you, and you can just try out many algorithms, including the ones I showed you. And you can see, I mean, the point I'm showing this is to say that although a lot of new methods have come out, SPO Plus still seems to be one of the best. And in terms of performance, here it's showing that SPO Plus requires very few calls to the optimizer, although there's benefits to other approaches too. And if you're interested in this field of contextual optimization, here are 2 excellent surveys. And these authors here have a lot of papers related to the problem I showed you and others on like how to deal with certain other issues that come up in terms of speed and practicality and different problem settings. So these 2 papers are a great starting point to for you if you want to learn more about these topics. Please check both of these out. All right, so that's my time. Here are the papers I talked about if you want to look them up. And I'm happy to take any final questions. Thank you so much.
Thank you so much, Adam, for very insightful presentation on Smart Predict and then Optimize. So if there are questions, I can see that a couple are already in the chat. And if you would like to ask them, say in person, we will give you the rights to the camera and the microphone. But I believe that you have 2 or 3 questions already in the chat.
So I'll go to Jojon's question. So basically, the question is like, are we worried that like SPO or decision focused learning is going to overfit the data to some specific optimization problem, and maybe MSE is like good enough. So this is something you should be concerned about, and so it's a good question. So actually, what you should do in practice is you should minimize a combination of both. That's what I always tell people. And by the way, people are using this in practice. So you like take a combination of the mean squared error and the SPO loss, and that works. That works really well. But of course, like if you need these predictions for many different use cases, then MSE is probably more robust. But if you just have one specific use for the predictions, then you should use SPO. And of course, it's a heavier weight. It's harder, it's not as easy to implement as MSE because it requires solving optimization problems. So it's more time intensive. So there are trade-offs, of course. But if you're at a hedge fund or you're at Amazon, that little difference can make a big impact. Patrick asks that fewer leaves generally improve interpretability, but do trees actually improve explainability? Are there situations where the results lead to unintuitive models? So I'm not gonna get into like are trees like, so there's a huge general debate if like are trees like providing intuition on what's going on. So I think it's understood that like trees don't give any notion of causality generally. And when we say interpretability, it just means like we could like print it out and show it to someone and they can follow the steps of what to do. That's all. But I guess more technical answer would be that we did show theoretically that the SPO plus solution converges to the least square solution. So like we don't expect really too big of like the differences would, I think, would not really be noticeable to a human in terms of intuition. Lewis asks, what happens if we have nonlinear objective? Okay, so it depends what we mean by nonlinear. But basically, in the nonlinear setting, we cannot come up with this SPO plus loss function because I'm really using some useful notions of duality and some properties of linearity. And if the parameters appear in a nonlinear way, like in a news vendor problem, for example, you don't want to just estimate a point prediction. You actually want to estimate the entire distribution. And so there are papers out there that talk about estimating distributions in a smart way, rather than just like minimizing, rather than just doing like maximum likelihood estimation, you might want to think about the downstream optimization problem as well. So I have a paper there, and there are several others on thinking about that. And let's see. So Stefan asked about like, do I predict all the cost parameters at once or one by one? You can actually do both, but it's without lots of generality, you can kind of just do them all at the same time. But you can also impose more structure on your prediction models if you want, just by adding a constraint to the model. Patrick asks, how does this compare to the perturbed potential Young losses? So those that it's a little too technical for the audience maybe, but I just think of those as alternate approaches to minimizing the SPO loss. Okay, so that one is, what it's trying to do is basically make the gradient non-zero by introducing some noise, and so therefore you can do some gradient descent. So so that approach and others, they try to basically create non-zero gradients, so you can run some like black box optimizers. Okay, I'm over time. Sorry if I missed your question, but you can always reach out to me. And I appreciate everyone's interest. Thank you so much.
Thank you, Adam, very much again. And to the audience, please remember that we will be back next week with another seminar. And please register to the mailing list if you would like to receive news from us. Okay, thank you so much, everybody, and see you soon. Thank you, Adam.